Hi, good morning. Today is December 20th, year 2012, and I'm staying in a hotel in Taipei, and this is my test run just before my public talk at the conference called ISAC 2012.
Is entitled Constant, Unary, Constraint, and Symmetry Real-Weighted Counting CSP by Yamakami.
Well, thank you very much for introduction. My talk is about the constant, unary, constraint, and symmetric real-weighted counting CSPs. And this talk is about the Boolean type constraint satisfaction problems, or we simply call it the CSPs. And particularly, we are interested in the counting version of CSPs. Well, in short, we call it the sharp CSPs. The sharp stands for the counting. And what we are talking about here is we will give you a new insight into the classification theorem for the real-weighted sharp CSPs. And why this is new? Because this work gives an alternative, a simple proof to the existing result of about approximation complexity of the sharp CSPs. So we start with the definition of constraint satisfaction problems. And the simple example is something like this one here. This is a logical formula in conjunctive normal form. This is AND of three ORs. And we actually think this OR as a function, so that we are calculating the multiplication of three OR functions. And for our CSPs, usually we have three different types of questions. The first one is there any satisfying assignment for this F? So the existence of satisfying problem is the either this is the part of the decision problem. And the second one is if you have the satisfying assignment for this F, then we are interested in how many of them. And the last one is, well, even though we know that the several assignment that satisfies F, but then also it's very hard exactly calculate the number. In that case, we resort to approximate such a number. And those are called decision CSP and exact counting CSP. The last one is approximation, approximate counting CSPs. And our talk is about the last item. The CSP problem can be represented by in a bipartite graph in the following way. We have two different columns here, and in the left side, the variables are attached to each node on the left-hand side. And the right-hand side, we attach a constraint. And all the edges are, for example, if you have or x1, x4, x3, then we have the lines at the edges from x1, x3, x4, connecting to this OR. And the first question is about the existence of assignment, satisfying assignment. That is actually the calculation of the multiplication of three ORs, and that's going to be 1. And if you want to count the number of the truth assignment, satisfying assignment, and we are actually summing up all of those products. So this value gives the total number of the satisfying assignment. And for more formally, we have the variables and the constraints. Those are given as an input instance. And we are going to calculate to determine the three questions as I presented before. And CSPs are not really special. That appeared in many different fields. For example, AI, database, graph theory, scheduling, and even in statistical physics. They actually didn't talk about it in a certain type of CSPs. The basic question we are actually facing is that whether we can efficiently solve all CSPs. Well, this seems to be still open. And we are actually looking for, well, we start with the explanation of the decision CSP here. Decision version of the Boolean CSPs are NP problems. And formally here, we are interested in a particular set of constraints, so that all the constraints appearing in this instance come from this F. The question is whether there exists a truth assignment for that satisfies all constraints given as an input. And the typical example of such CSPs are satisfiability problem and vertex cover problem and so on. And if you look at all the NP problems, and according to the Radner's result, assuming that P is different from NP, and we have infinitely many different levels, complexity levels. The bottom line is the polynomial time computable problems. The top of this the world is NP complete problem, and in between we have infinitely many distinct levels. But if you look at the world of CSPs, there is only two levels. And either a problem is polynomial time solvable or NP complete. Nothing else. So that's the kind of very interesting part of the CSPs. Now we are looking at the counting version of the CSPs. And sharp P is the variant class of the counting problems. And counting version of CSP is formulated in this way. So the instances are pretty much the same, the Boolean variable and the constraint. That's actually taken from this particular set F. So F is actually given as a fixed set of constraints. And we are actually calculating the total number of the satisfying assignment that satisfies those constraints given as an input. So examples of this counting version of CSPs are the sharp SAT and sharp downset. This is the downset problem, and this is the bipartite independent set problem. We are simply counting the number of the bipartite independent set. So now we move on to the more general real-weighted sharp CSPs. Well, instead of putting the or and, those kind of Boolean functions, we are actually putting the any real valued function here. And here we have still Boolean variables here, but the outcome of those constraints are now real numbers. So what we are going to calculate is similar to the before, summation of all those products. So that you just simply multiply all the result of those constraints and then take all possible combination of Boolean variables, Boolean values. So that the sharp CSP is simply take this formation. This formulation is called the constraint frame. So that the constraint frame is given, then we are going to calculate this value, CSP sub-omega. Now, as the title said, we actually use the unary constraint. The unary constraint is a function of the one variable. So if you look at this graph here, there is you see that in red marked nodes. Those are unary functions. And particularly, we recognize two special unary constraints called a constant unary constraint, delta 0 and delta 1. That represent 1 and 0. So now we move on to the approximation scheme here. So we are going to solve the sharp CSP using an approximation scheme. So that the one kind of approximation scheme we're going to use, this is a randomized approximation scheme, or RAS. We have the input x, so this is actually true input, and epsilon is the parameter specifying the error. And this is the target value f of x, and this randomized algorithm output w with the high probability that actually approximate f of x with relative error 2 to the epsilon. Relative error means the absolute value of the f of x is bounded by two w's with with the factor of 2 to the epsilon. The important thing here is, even though that an alpha beta are approximated, but then an alpha plus beta may not be approximated. So that's the kind of a little tough part to deal with this approximation scheme, because we are dealing with plus number and the minus number. Well, in a complex case, the situation is a lot more complex. Now we have to compare two counting problems. So we will use an AP reduction. And this is the approximation preserving reduction introduced by the Dyers and Goldbergs and Greenhills and Jeremy in the year 2003. And basically, if is AP reducible to G, we have an Oracle probabilistic Turing machine, and that satisfies that randomized approximation scheme, and compute G, compute F using G as an oracle. So we will use a special notation here. It's an F is reducible to G using this less than or equal notation. And if you look at an earlier result, early example, there's the sharp downset. This is the counting of the number of the downset. This is equivalent to the number of counting the bipartite independent set problem using this AP reduction. And those are actually reducible to sharp SAT. So approximating sharp CSP is the, we have the number of the result here, starting with the year 2010. It's Dyer, Goldbergs, and Gelsenius, and Richard B. They proved the complete classification for the Boolean problem. But they only talk about an unweighted Boolean sharp CSP. Unweighted means that the constraints are actually putting out either 0 or 1. So now that is generalized into a complex weighted constraint. I gave up the classification theorem for all possible and complex weighted Boolean sharp CSPs. Here, this is actually look up, well, this is the very simple picture that's showing that in the trichotomy theorem, proven by Dyer and et al. They showed they classified all sharp CSPs, unweighted sharp CSPs, into basically 3 levels. The bottom case is polynomial solvable sharp CSP, and the top level is sharp B complete problems. And in between, there are possibly at an intermediate level. The possibly means that this borderline is not that clear. We need some kind of structural complexity theoretical assumption. And if you look at the complex weighted case, using this U stands for the set of unary constraint. So we allow the machine to take all possible unary constraints for free. So in that case, we only have the 2 levels. The bottom case is polynomial solvable sharp CSPs, and the top levels we have the sharp B complete problems. So I'm concluding this talk and giving my result here. So unary constraints are free of charge. As I said, all those results showing before, for example, here and here, those results are actually using unary constraint for free. So our goal here is to get rid of this big U notation. And those unary constraints are freely used in so many results. One reason is that if you use this unary constraint, the proofs for the classification theorem is much easier. And also that the proof itself is kind of the cleaner. So in this talk, I'm going to give an alternative simple proof for the classification theorem to specify that where those unary constraints are necessary and where those unary constraints are eliminated. To do so, now just take a look at it in a symmetric constraint. Symmetric constraints are the very simple constraint. That depends on the value of the value of the inputs, but it doesn't care about the order of the variables. For example, if you have three variables defining f, then f only depends on where we have 1, where we have 2. How many ones and how many ones here. So that it doesn't matter whether we have the 1 at the end or in the middle or the first. So if you restrict attention to the symmetric constraint, then the earlier dichotomy theorem can be simplified. For example, we just take a look at it in the dichotomy theorem. This is the more formal form of the dichotomy theorem here. F is the complex valued set of constraints. And if F is contained in ED, then ED stands for the equality and the disequality. So that's the very simple set of constraints that's consisting of equality and the disequality. Then sharp CSP is very easy to compute. Otherwise, then sharp CSP is very hard. It can be much harder than the sharp SAT. And our goal is, as I said, that we want to eliminate this particular use of U. So take a look at the proof. And if you just take a close look at the proof here, that if F is in ED, then a sharp CSP of F and U, then U stands for that set of unary constraints, right? This is the polynomial time solvable, but if F is not included in ED, then we just choose F that is not in ED, and then we have to have the many different cases. Now this is a case-by-case study, and then finally we'll arrive at this conclusion. And using this particular result, then we get this hardness result here. But if you take a look at this whole entire proof, it takes something like 20 pages, but it's really hard to say where we need U and where we don't need it. So what we are going to do here is to specify where and how we need those U. To explain, to describe our result here, I'll just introduce the notation here, and the bracket notation. x1, x2, x3, this is actually the vector form of expressing the outcome of this function f. So that f can be represented by this vector notation. For example, here, the OR function is actually represented by 0, 1, 1, and is 1, 1, 0, and equality is 1, 0, 1. So this is actually a very succinct notation to express the function. So this is the result I'm going to present this talk. We have a theorem that's pretty much the same as the original classification theorem, but if you look at this flowchart here, the conditions seem to be a little more awkward. But if F is contained in the DG or an ED1+, in this case, sharp CSP with F without U is polynomial time solvable. So U is also polynomial time solvable. So we actually get this result. And another condition here is if F is included in DG minus ED1 union AZ, the definition of those classes, those sets are a little complex, so that take a look at the proceedings. And then we get the same result. But we can't combine two of them. So that's the tricky part. And if we don't have those, if the F does not satisfy those conditions, then we get the following result. There exists a particular constraint called G that appears in either B or OR. The OR is the extension of the standard logical OR, so that means 0xx. If x and y are equal to 1, so 0, 1, 1, so that exactly is an OR function. Okay, the other one is they are a lot more complex. We have an x, y, z, and x, y, z are not 0, but an x, y, x times z does not match y squared. So this is the special condition. So G is either this form or this form. And that satisfies the lower bound of this sharp CSP of F. And using this result, adding U, we actually get sharp SAT is the lower bound of the sharp CSP of F and U, using this result as before. So that up to here, we don't need U. But at the very last moment, to get this lower bound result down to the sharp SAT, we really need U. So to reach the ultimate goal of ours, that means that we actually totally get rid of this U and get the classification theorem. But the previous result only requires the U at the very end. So that the next challenging point might be how to get rid of this U to supplying more conditions, and then to get the totally complete classification theorem without U. Well, thank you very much.
Thank you. We are sort of out of time, so I'm sure the speaker will be happy to take your question after the talk. Let's thank the speaker again.